So let me start our session. Is my screen is visible? Is my screen is visible?
Yes, sir.
Yes, sir.
Ah, yes, right. Correct. Fine. So last two classes we discussed about the as standard cycles, right? So in the as standard cycles we discussed what is Otto cycle, what is diesel cycle, how it performance differs, and how we can calculate the efficiencies, right? So we discussed these two cycles, right? Otto cycle and diesel cycle. And this class we are going to see about the dual combustion cycle. This class we are going to see about the dual combustion cycle, right? This dual combustion cycle is combination of Otto cycle and the diesel cycle. Otto cycle and the diesel cycle, right? So once again we refresh the what are the terms we discussed in earlier class, okay, right? So first one, the assumptions, right? So why we have to repeatedly informing you these assumptions are important for the as standard cycle means it's an important question, right? So for the as standard cycles, what are the terms are important, right? So the first term is the working fluid, right? So the working fluid is a pure air with constant specific heats. Pure air with constant specific heat. Pure air means the ideal gas, right? So the ideal gas will be used as a working fluid in a as standard cycles with constant specific heat, and the mass flow rate is a constant. The fixed mass flow is there in entire cycle. The fixed mass flow, right? Then the combustion process is replaced by the heat transfer process, right? So for the Otto cycle, the heat transfer process in the process of the constant volume process. In the constant volume process, we can add the heat. The heat addition will be in constant volume process, as well as in diesel engines, the heat addition takes place in constant pressure process, right? And all the cycles, right, all the process are considered as the reversible process. All the process in a cycle are considered as a reversible process. Then the expansion stroke as well as the compression and expansion, right? The compression and the power strokes will be considered as the adiabatic process, reversible adiabatic process, or an isentropic process. So we are using that formula that is P V power gamma is equal to C, right? So PV power gamma is equal to C, right? Then there is no chemical change, right? There is no chemical change in that cycle, right? It's an important term, and the cycle is considered as a frictionless. So the efficiency is automatically increases, right? So due to the friction, the efficiency may reduces, but here we are considering that it is a frictionless. So there is no wear and tear, vibrations, that and all, right? So it is Otto standards, Otto cycle, right? So here we consider the four process. So here the process are same in the entire all the cycles: Otto cycle, diesel cycle, and dual combustion cycles, right? So the 1 to 2 is a adiabatic compression, adiabatic compression process, or isentropic compression process. Then the 2 to 3, it is for the Otto cycle. 2 to T, it is for Otto cycle. The heat is addition. The heat is added in constant volume process. The heat is added constant volume process, and the expansion 3 to 4 is a adiabatic expansion, right? Adiabatic expansion process, and the heat rejection, that is the fourth process, is the heat rejection process at constant volume, right? So we discussed about the how the efficiencies are calculated, how you can derive the equation for the thermal efficiency, right? So for the Otto cycle, it is the as standard efficiency or thermal efficiency. Right. So here one more point is important, right? So how the thermal efficiency will improve, right? How the thermal efficiency is improved? It is the thermal efficiency improved by the two categories in this graph. In this graph, we are mentioning the two categories, right? One is the compression ratio, right? So once the compression ratio increases, the thermal efficiency increases, right? So the graph will be like this, right? So the compression ratio increases, the thermal efficiency also gradually increases. And second term is the adiabatic exponent. The adiabatic exponent increases, the thermal efficiency also increases, right? So for the gamma value, right? So for 1.2, 1.3, 1.4, 1.5, like that means the efficiency will increase, right? So these two we have to remember. Then the diesel cycle, right? So in the diesel cycle, instead of the Otto cycle, the heat addition only the difference, right? So here the heat addition will be in constant pressure process. Here the heat addition in constant pressure process, right? So this only a difference. This only a difference. Remaining and all same for the Otto cycle. Remaining and all same for the Otto cycle, right? So here we can add one more thing. What is that means? The cutoff ratio. Cutoff ratio. What is that cutoff ratio, right? It is the ratio. Cutoff ratio is a ratio between when the fuel is supplied and when the fuel is cut off, right? So where at which volume the fuel gets cut off, that is the V3, right? So here, right? So for the 3 point, here the volume will be 3, right? So the cutoff ratio means volume 3, volume 3 divided by, so where we can supply the fuel, at which volume we can supply the fuel starts, right? So for the point 2, right, from the point 2 we can supply, we can start the we can start to supply the fuel to the system, right? That volume is called V2, that V2, right? So the ratio between these two volumes is called as the cutoff ratio. These two volumes is called as cutoff ratio, and efficiency we can obtain by the efficiency like this, right? In the terms of the compression ratio as well as the cutoff ratio, right? So this one is called as the efficiency of Otto cycle, and here we can add some more things. Some more thing that is called as a K factor. That's called the K factor, right? So the efficiency of the diesel engine, the efficiency of the diesel engine is less than the Otto cycle for the same compression, right? So the efficiency of the diesel engine is less. That is, the Otto cycle efficiency is greater than, sorry, is greater than the diesel cycle for the same compression ratio, for the same compression ratio, right? So you can remember this one, right? So the efficiency of Otto cycle is more while comparing to the diesel cycle at the same compression ratio, right? So now in this class we can see the dual combustion cycle. Dual combustion cycle. A dual combustion cycle is a combination of the Otto cycle and the diesel cycle, right? It is the combination of Otto cycle and a diesel cycle. Just a minute. two more members absent, right? Two or three members absent, I think. Correct. So is my screen is visible? Is my
Yes, sir.
okay, right, fine. So the dual combustion cycle is the combination of an Otto cycle and a diesel cycle, right? So why we are telling that the combination of these two cycles, that is the Otto cycle and the diesel cycle. For the Otto cycle, the heat addition takes place in constant volume, right? Right. So here the heat addition is the partial heat addition. The partial heat addition is takes place in the constant volume process, and some partial heat addition takes place in the constant pressure process, right? So for the constant volume process called as Otto cycle, and constant pressure heat addition process called as diesel cycle, right? So in this dual combustion cycle, we have two types of heat addition: the partial heat addition at constant volume, as well as the partial heat addition at constant pressure also, right? So it is called as the dual combustion cycle, right? So one more type, it is also called as a semi diesel cycle. It is all called as a semi diesel cycle, right? So the remaining process are all same. The remaining process are all same, but here we have five process. Here we have five process, right? So the first process, that is the point 1 to 2, right? Point 1 to point 2, it is compression process, that is adiabatic compression process, right? So we are using the P V power gamma is equal to C, right? So adiabatic compression process, and here we have a compression ratio. What is that compression ratio, right? So before the compression, what is its volume, and after compression, what is its volume, right? So here our compression ratio is V5 by V2. V1, sorry, V1 by V2. It is the compression ratio, right? Then process 2 and 3, it is the partial heat addition process at constant volume, right? So it is the heat addition process, right? See, here it is the heat addition process at constant volume, 2 to 3. Then 3 to 4. 3 to 4 is a constant pressure process. So here also some heat addition are there, right? So heat addition, constant pressure process, right? Then 4 to 5, it is the power stroke. It is a power stroke, that is the reversible adiabatic expansion process. Reversible adiabatic expansion process, or a isentropic expansion process. So here also we are using the same, right? PV power gamma is equal to C for the process of 4 to 5. The process of 4 to 5, this is isentropic or reversible adiabatic expansion. And 5 to 1, it's a heat rejection process. 5 to 1 is a heat rejection process. Here the heat rejection will be in constant volume, right? So all the process, Otto cycle, diesel cycle, and dual combustion cycle, right? So whatever may be the Otto standard cycles, right? So this at standard cycles, the heat rejections takes place at constant volume. The heat rejection takes place at the constant volume, right? So these five processes involved in dual combustion cycle, right? Then, so it is the PV diagram and TS diagram for the dual combustion cycle, right? So process 1 to 2, it's a adiabatic compression, and process 2 to 3 is a heat supply, that is the heat addition process partially at constant volume, that is Q1, heat addition Q1. And here the same, the one more partial heat addition takes place at constant pressure, that is 3 to 4, 3 to 4, right? Then 4 to 5 is a adiabatic expansion, and 5 to 1 is a heat rejection process, right? So here we can draw a TS diagram, right? So first point 1 to 2, point 1 to 2 is a compression process, right? So while compression, what will happen? The pressure increases, at the same time the temperature also increases, right? So at point the process 1 to 2, the process 1 to 2 is adiabatic compression process. So due to compression, the temperature gradually increases, right? So the T1, here the T1 is low and T2 is somewhat higher than the T1 temperature, right? So at the time the entropy is constant. At the time the entropy is constant, right? Then 2 to 2, 2 to 3 process. 2 to 3 process is a partially heat addition at constant volume process, right? So here it is volume is constant, right? So this curve indicates the volume constant, right? Right. So here some partial heat addition is there, right? Partial heat addition this is there. So the temperature increases. So the temperature of the system is increases, right? So the temperature T, so the temperature increases, right? So once the temperature increases, the entropy, the changes in entropy is there, right? So the entropy is a function of the temperature. The entropy is a function of the temperature. So the entropy also may varies, right? So here S3 entropy, S3 entropy, right? Again the heat is added. Again the heat is added to the system by constant pressure process, right? So what will happen? Again we have to add the heat at constant pressure, right? Here the pressure is constant, right? See, this curve is different, this curve is different, right? So it is the constant volume process, and here it is the constant pressure process, right? So this point is the third point. This is the third point. This is the third point, right? 1, 2, 3, and 4, and the 4, right? So where the maximum temperature is there at the T4, it's a maximum temperature T4, right? So here the curve, see, this curve is different, this curve is different, right? So it is the volume constant process, and here it is the pressure constant. Then here same, volume is constant, right? So after that, the 4 to 5, the expansion process. The expansion process, the pressure decreases as well as the temperature also decreases, right? So the pressure decreases and the temperature also decreases at T5. Then the heat rejection process, the heat is rejected to the atmosphere, right? So the temperature is gradually reduces, right? So at this point, the entropy T4, sorry, S4 is equal to S5, right? So it is the PV diagram and TS diagram for the dual combustion cycle, right? So then we can see how we can get the efficiency of the dual combustion cycle, right? So uh, for the for the assumption of the air standard cycles, the mass flow rate, the fixed mass is there. That's the first assumption, right? So the fixed mass, so we can consider the mass flow rate is 1 kg of air, the mass flow of the 1 kg of air, right? Then what is the heat addition? We have a two heat addition process, one at constant volume and one at constant pressure, right? So one at the constant volume and one at the constant pressure, right? So in this PV diagram, see, right? So 1, 2, 3, 4, and 5, right? We have 5 process, right? So process 2 to 3, process 2 to 3. So here P, right? So it is the constant volume process, right? So it is the constant mcv and the temperature difference. What's the temperature difference? T3 minus T2, right? It is the heat addition. It is the heat addition, that is Q1. Q1 is mcv. Here we can consider the mass is 1 kg. So we can neglect that, right? So Cv, the temperature difference. And one more heat addition is there. One more heat addition is there at constant pressure process. And constant pressure process, the heat addition, right? So here the mcp, what is the temperature? So T4 and T3, T4 and T3, right? So the total heat addition is the combination of these two, right? So that is the here Cv T3 minus T2 plus Cp T4 minus T3. Here somewhat wrong, right? Right. So the heat addition, right? Heat addition at constant volume as well as the heat addition at constant pressure, right? We have to add these two terms. That is the total heat supplied to the system. That is the total heat supplied to the system. And what about the heat rejection? What about the heat rejection? It is the in constant volume process. It is the constant volume process. Then the temperature difference T5 minus T1, right? So the heat rejection is at the constant volume process T5 minus T1, right? So generally, what is the work done? Work done is how much amount of heat supplied, the difference, right? The difference between the how much amount of heat supplied and how much amount of heat rejected, right? So that difference, that is the Q1. So that is a Q in minus Q out. Q in minus Q out, right? So here the Q in is the Cv T3 minus T2, right? Cv T3 minus T2 plus Cp T4 minus T3. Cp24 minus T3 minus the Q out. Right? Then what is meant by efficiency? Generally the efficiency is output by the input, right? So here the output is the work done, right? So work done by the heat supplied, right? So that is called the as standard efficiency, work done by heat supplied. So here the work done, right? The same, this formula, this terms we can take as a work done, and the heat supplied, it is the heat supplied. It is heat supplied, right? So we can divide these terms, right? So we can simplify this one. So 1 minus Cv, that is, so this term and this term will be cancelled. 1 minus these terms, right? So 1 minus Cv T5 minus T1, this term divided by the whole term. Again, we can remove this Cv, that is the whole term will be divided by the Cv. So Cv by Cv, so it is cancelled. Cv by Cv, it is cancelled here. Cp by Cv, right? So we already know that what is that Cp by Cv? Cp by Cv is the adiabatic exponent, that is gamma, right? So we can replace here, it is the gamma. So 1 minus T5 minus T1 divided by T3 minus T2 plus gamma T4 minus T3, right? So it is the efficiency of dual cycle. It is the efficiency of dual cycle in the terms of the temperature. Again, we can simplify in the terms of some modifications, right? So here we have 3 ratios. So one is the compression ratio. What is the compression ratio? Before the compression, what is its volume, and after compression, what is its volume, right? That ratio is called as the compression ratio. And the pressure ratio, here it is P2, right? So at the constant pressure process, the P3 by P2, right? Both are the same. So the pressure process is 1. The pressure process is 1. Then the cutoff ratio, right? So at what volume the fuel will be cut off and what volume the fuel will be supplied. That ratio is called as the cutoff ratio. By using these ratios, we can derive thermal efficiency of the real combustion cycle. So we already know that the process 1 to 2 is adiabatic compression process. So we are using that formula, the PV power gamma. PV power gamma is equal to C. PV power gamma is equal to C. Right. So in Otto cycle, DC cycle, right, all the cycle we can derive the same. We can derive the same formula, right, which is we can study earlier, right? So here the T2 which is equal to T1 into compression ratio power gamma minus 1, right? So the T2 temperature in the term of T1, right? The T2 temperature we can take as a in the form of T1, as well as the same we can use for the adiabatic expansion, adiabatic expansions, right? So at the constant volume process, so P, so volume will be same and P is directly proportional to the temperature, right? So the P2 by P3, which is equal to T2 by T3, T2 by T3. So the T3 is in the term of T2 into the pressure ratio. What is the P3 by P2 is a pressure ratio, right? See here, P3 by P2 is a pressure ratio which is denoted by RP, right? So that same you can use here, right? So P3 by P2 is a RP. So T3 by T2 is a RP, right? So T3 in the terms of T2, T3 in the terms of T2. Again, we can substitute the value of T2 in the terms of T1, right? So T2 is equal to T1 compression ratio power gamma minus 1, right? That same value will be substitute here, right? So the T3 in the form of T1, T3 in the form of T1, right? Then the constant pressure process. So the volume will be directly proportional to the temperature. Right? So that is called the Charles law, right? That's called the Charles law, right? So V3 by V4, which is equal to T3 by T4, right? So here, what is V4 by V3? That is the cutoff volume, right? So at the right, see here, so it is the cutoff volumes, right? So V4 by V3, it is called as the cutoff ratio, right? So that cutoff ratio is denoted by RC, right? That cutoff ratio is denoted by RC, right? That RC will be inserted here. So here the T4 in the terms of T3 into RC, then we have the value of T3 in T1 substitutions, right? So we can substitute the value of here instead of the T3, right? So for the expansion process, the same T5 by T4, right? T5 by T4 is a compression expansion ratio. Here the expansion ratio. What is the expansion ratio? Right, the expansion ratio is the ratio between after the volume before the expansion and the after the expansion, right? So V4 by V5 power gamma minus 1, right? So here we can add and divide the volume V2, right? So its value will not change, right? So here, what is V4 by V2, right? In this diagram, V4 by V2, right? So here V4 by V2, right? V4 by V2, it is called as the cutoff ratio. V4 by V2 is called as cutoff ratio, right? So the V4 by V2, this is called as the cutoff ratio, and V2 by V5, V2 by V5. Right. Here V2 by V5, it is the inverse of the compression ratio. It is the inverse of the compression ratio. Generally, the compression ratio is V1 by V2, or here the V1 value, which is equal to V5 value, right? So V5 by V2 is the compression ratio. It's a compression ratio, but here we can use the reverse, that is V2 by V5, that is the compression ratio, right? So for the isentropic expansion process, we can write in the terms of the cutoff ratio as well as the compression ratio, the cutoff ratio and the compression ratio, right? So the T5 by T4, T5 by T4, which is equal to T4 into this term, T4 into this term, then the T4 will be replaced by this. The T4 will be replaced by this, right? So the all the values T2, right? See the T2 value, T3 value, and T4 and T5, right? So all the values in the form of T1, which is represented in the form of T1. So we can substitute all the values in the thermal efficiency, all the values in the thermal efficiency, that is T5 in terms of T1. So automatically the T1 will be cancelled. So we can obtain the thermal efficiency as like this, right? So we can substitute all the values in the terms of T1, right? So we can obtain the dual cycle efficiency as like this. Is it clear? Anyone having any doubt? Anyone unmute? Ganesh Kumari?
Yes, sir.
Okay. Do you have any doubt?
No, sir. No, sir.
No. So we can proceed, right?
Yes, sir.
Okay. So the comparison, right? So how we can compare what is the efficient, which cycle efficiency is more, right? Like that we can see, right? So in this PV diagram, see, 1 to 2 is the same for all the process, right? So 1 to 2 is the same for all the process, right? Here see 1, 2, 3, and 4. What is the cycle? It indicates the both are the constant volume cycle. So it is the Otto cycle. It is the Otto cycle, right? 1, 2, 3, 4, right? So the same corresponding TS diagram here, right? 1, 1, 2, 3, and 4. It is the Otto cycle. And for the same, what is diesel cycle? What is diesel cycle, right? So here, see, the compression ratio is same, right? So we are seeing here for the same compression ratio, and same heat put, the same heat input and same compression ratio, we comparing these three cycles, right? So the compression ratio 1 to 2 is always same for all the cycles. We consider the 1 to 2 is same for all the cycles, right? So we can't change it, right? So the difference between the Otto cycle and the diesel cycle here, first we can differentiate Otto cycle and diesel cycle, right? So here the third process will be the constant volume, sorry, constant pressure process, right? So what will happen? The curve will be like this. The curve will be like this. See, the curve will be like this, right? So by comparing these two, Otto cycle and diesel cycle, in this TS diagram, which one is the temperature difference is more? Which one is the temperature difference is more in the heat addition process? Whether, see, in the Otto cycle, here the T3 is there, and the diesel cycle, here the T3 is there. It is for Otto cycle and it is for the diesel cycle, and here the 2 point is same, right? So which one is the heat difference is more, either Otto cycle or diesel cycle? Anyone?
Auto cycle,
Otto
sir.
cycle temperature is more, right?
High.
That is the difference between these two temperatures, that is the T3 minus T2 and T3 dash minus T2, right? So which one is the difference is more? See here, the difference is more, right? So where the temperature difference is more, there the efficiency is more. There the efficiency is more. So while comparing the efficiency, which one is efficiency is more? Otto cycle efficiency is more than the diesel cycle efficiency. And what about the diesel? So what about the dual cycle? What about the dual cycle? It is the between, that is the efficiency of the dual cycle is between the Otto cycle and the diesel cycle, right? Between the Otto cycle and diesel cycle. Is the diagrams clear? See,
Yes, sir.
okay, right? So for the Otto cycle, the efficiency more, dual cycle is comparatively lower than the Otto cycle. Then the diesel cycle efficiency is comparatively very low while comparing these two cycles for the same compression ratio and same heat input. Is it clear? Is it clear?
Yes, sir.
Okay, right.
Yes, sir.
Okay, right. So the same we can write here, right? So for the same compression ratio, right? For the same compression ratio, right? See which one is the temperature difference. That is here the temperature is common, right? Here the temperature T2 is common, and here see V6 on temperature is there, and V4 on temperature is there, and V7 on temperature is there, right? So the temperature between the T6, right? The 6, what is the 6 value? 6 value is the Otto cycle value. Then what about the 4? The 4 is a dual cycle and 7 is the diesel cycle. So the efficiency in the form of like this, right? So the efficiency of Otto cycle is more than these two cycle, that is dual cycle and the diesel cycle, right? So is it clear? Is it visible? Right? So the efficiency of the Otto cycle is greater than the efficiency of dual cycle and the efficiency of the diesel cycle. The efficiency of diesel cycle. Is it clear? For the same compression ratio and for the same maximum pressure and temperature, for the same maximum pressure in this term, it will be reversed. It will be reversed, right? See the graph. So 1745, 1745. Which cycle is this? Bhuvaneshwar. Bhuvaneshwar.
Hello, sir.
1745. Which cycle is this? See 1 to 2. It's adiabatic compression and constant pressure. Constant pressure means it's a diesel cycle, right? So 1745 is a diesel cycle and 16 is a 16 is the Otto cycle.
Auto cycle, sir.
And here it is dual combustion cycle. It is here dual combustion cycle, right? So for the same maximum pressure and temperature, the diesel cycle efficiency is more. The diesel cycle efficiency is more while comparing to the other two efficiencies, other two cycles, right? So is it clear? So we can finish. Sorry, we can finalize this class. We can finalize this class.